Our office is growing. We're moving beyond a single building location with one network closet into multiple rooms and multiple buildings. By the time we're done here, you will be able to design switch connections for a highly available mid-size office environment. I'm so excited because it's time to grow beyond a small office environment. See, up till now, we've had all of our perspective in what I'm calling Suite 4, the office that we actually built an entire cabling series around. We moved in, we wired new ports, we installed switches, and even in the last nugget, we talked about connecting those switches together. 2 switches in the same rack. Going beyond just using a single connection and talking about the impact of spanning tree and link aggregation ports and the consequences of using an unmanaged switch. And now it's time to expose the rest of the story. Suite 4 is actually an expansion suite of the main office of the company that we're working with. And now I want to take you over to Suite 1, which is actually the larger office, and begin getting you in the mindset of graduating beyond our small network design into planning to build a mid-sized network environment. Well, this is the office that we know and love. We built this in the cabling series, installed the rack, did all the cabling, installed the switches, and got this office connected. But now it's time to go into the great beyond. Come with me. Walk into this area, which is the shirt company, and down the hallway and out the front door. Now, when I showed you the map of the office suites, I had a couple that are question marks. That wasn't door prizes. Those are just tenants that I have no idea who they are. So we're going to walk right on by them into that Suite 1 down at the end. And here we are. Turn on a few of the lights. There we go. And let's come into the, what I would call the MDF of this organization. We close the door. Looking up there, we've got some work to do. So this was the one that was originally powering this company. And if I look right here, I see there's a battery backup sitting in the rack. There's a little server going right here. Looks like a DSL modem shoved right here. There's a cable modem mounted on the wall over there. So a couple internet connections coming in. I see switches, routers, and just a big old cabling mess. Now, if I stand on the chair here, because this thing is not within arm's reach, I can see that there's actually a router sitting right here, as well as 2 different switches and patch panels galore. So this office is actually connected to the other office with, right now, 2 Ethernet cables that are running across the ceiling, through the rafters, over the other 2 mystery companies, and down into that expansion suite. Now, the irony is, even though that other office space has a larger room, I would consider this the MDF. And the reason why is because this is where the router actually lives, as well as where the internet connections come in, and where most of the connections are terminating. Now, we could make the other office suite the MDF because it is just a label, but at a gut level, I would say that would require us to move all the internet connections over there, which would be a cost because we'd have to have all the carriers come out and move all the cable modems and DSL modems and everything else feeding this organization. And if nothing more, Suite 1 just has a feel of the MDF. It's central. If this business grows beyond that second suite into other suites of this office complex, this would be the central hub where everything would come back and connect to. So now here's the dilemma. I'm looking here and we've got 2 switches that are connecting this office and connections that are running over there. This is beyond just connecting 2 switches together with redundant connections. How should we connect these 2 switches to those 2 switches? Well, you could just start daisy chaining those switches together, which is what I call a model of non-design. Take the 2 switches in Suite 1, connect them together, run a line over to Suite 4 down there, connect those together with 1 cable, and now you have this long chain of switches, which in the end leaves your network typically looking like this, because you're just plugging things together to make it work. And work it does. As a matter of fact, if you have unmanaged switches, meaning switches that don't support spanning tree, you have to go with a design like this. Because if you implement any kind of redundancy, a line like that or a line back like that, or running 2 lines over between the 2 offices, you cause a loop in the system. Since there is no spanning tree, there is no lagged in the unmanaged world. Or you can get managed switches and go with an intentional design. The first intentional design for switch port connections is known as a single core design. This is where you elect 1 switch to be considered your core, and all the other switches connect there. It's like the old saying, all roads lead to Rome. In this case, all of our roads lead back to the core. Now, I want to make sure that I'm bridging the logical view, which is what's shown in this picture, with what is physically happening in the building with the MDF and the IDF. So I'd like to ask you the question, if you were to physically map this out in your mind, where do you think the MDF and the IDF would be of this building? Pause the video if you need to think about it. I would suggest that this would be the MDF, and these switches down here would be in the IDF. Now, depending on the building, it might be two different IDFs, IDF 1 on the left, IDF 2 on the right. Or in the case of the office that we're working with right now, both of these switches could be in the same IDF. Now remember, the MDF and the IDF are just locations. They're names that we assign to places in our building that mean something to us. My youngest son's name is Nehemiah, but I call him Neo. I do that because it's easier to say, and I love the movie The Matrix. He is the one. So I've assigned some value to that name. But I could call my son Frank. He'd be confused for a while, but he'd get used to it. If the label Frank has some value to me, some deep meaning, then I'd do it. So usually the MDF is the room that holds most of your servers. It's the room where the internet connection usually comes in. It's usually the room most central to your facility. In the case of the building that we're working with, the MDF will be that messy room that I just showed you. Now, that's not the biggest room, but it's the most central room, and it's where all the internet connectivity comes into place. So that will be where we design our core switch. Now, I want you to see something here. Look at the connections coming from the core switch to these secondary switches. By the way, in the industry, they usually call these access switches. Just think of it as that's where things access the network. I chose to connect them with two cables. And I'd have the question for you, how do you think spanning tree protocol plays in all of this? If we left everything at default, which means spanning tree is normally on, what's going to happen? Well, I'll tell you what'll happen. Spanning tree will look at this network and realize that a loop is possible. Remember, if a single broadcast comes out and goes down this line, that broadcast is going to loop back around and back around and back around. So spanning tree will step in and disable one of those connections. It's going to do the same exact thing on the other side over here. It's going to see a loop potential there and disable one of those connections. So do you think that there would be a benefit to us in using link aggregation at all? Absolutely. I would take these and bundle them into two aggregated links. Now, to make sure that you follow, link aggregation doesn't allow you to bundle all of those connections into one big link. This is only between directly connected switches. So I could make two bundles of two, one here and one here. That way, spanning tree doesn't have to come in and disable one of those links, and I actually can use more bandwidth between those switches. Do you understand why that management is so critical? These types of things have to be configured. They don't just happen. Now, I want to bring this back around because I have a superpower where I can feel the questions going through your head. You're going, okay, I get it. Now we've got the MDF, but how does this relate to what we just saw in the actual office? I mean, there was two switches in the MDF, right? So where does that second floating switch go that's out there? That's a great question. And I'll even chase that with a question of my own. What happens if this core switch goes down? Yeah, that's really bad. Everything else is going to go with it because you lose that core. These guys are now little severed limbs. They can't reach the internet. Business stops. And that's why the single core design is only good for the smallest of networks. We've got a single point of failure, and that's not good. For that, we want to move to a dual core design. Oh yeah, that's awesome. So where's the MDF and where's the IDF? You feel it right now, right? MDF right there. That's our two switches. Notice they're tied together resiliently, redundantly. We have these guys that are sitting in the IDF. So to tie this back to our physical network that I walked with you a moment ago, this is suite 1. This is suite 4. Look at what we've done. We've got those two switches that we have in the MDF cabled redundantly. They're not only connected together with redundant links, which would make a great lag between those two switches, but look at the cabling that we can run over to our suite 4. We've got our suite switches right here connected to the two cores. So let's play out the scenario. Chunk, thing gets unplugged. I was thinking back to the tour that we did at the beginning. Did anybody else see this and go, what is that? Seriously, that's terrifying for a network environment. I'm assuming we've got internet connections plugged in there, switches plugged in there. Maybe that's the fire alarm, I don't know. But it surely isn't good. We're going to need to do some power rerouting as part of this project. But like I was saying before, in that current design, it surely isn't going to take very much for one of those switches to go down, but look at what happens. This connection fails, this one comes up, and we're routing out to the internet just as if nothing happened. Yes, we do lose some devices. If we have devices plugged into that switch, and they don't have a connection elsewhere, that's Sally's computer, that's the wireless access point powering half of the building. You're going to lose some stuff, but the business as a whole stays online. Now you might be thinking to yourself, okay, well, what size of business do I have to reach before I can justify going from a single core to a dual core? And that is a great question, but it's not quite the right question. The size of business doesn't necessarily matter. It's what does failure cost you? You might have a 1 or 2 person company, and maybe you've come up with a brilliant website. And if that website were to go down for an hour, you would lose half of your clients. That's a pretty high cost of failure. You could also have a 50 person company where most of the people are outside digging holes because you have a hole digging company. If the network goes down, that's all right. It'll come back up. Hey, Harvey, stop surfing the web. Go out and dig a hole. You see what I mean? You have to think about what is the cost of all employees not working because their computers stop functioning? What is the cost of missed customer opportunity because the customers couldn't get to your website or your people couldn't call out or your phone system went down because it ran on voice over IP? What is the cost of losing existing customers because you can't service their needs? And all the other overhead that runs your company that you still have to pay, but your business has stopped functioning because the network is down. These are some examples of hard cost calculations. And I'll tell you, for most companies, it doesn't take too long before you say, you know what? I think I'm going to throw another $1,000 switch in there. Because 1 hour of downtime would cost us probably triple that or whatever your business model is. Now keep in mind, I'm talking hard costs here. But there's something that happens to employee morale when that spreadsheet they were working on is lost and they have to redo it. Or they were in the middle of closing a deal and the screen sharing stopped. Those are things you can't quite put a hard cost around, but they do have impact. Now I don't want to leave this dual core design picture without answering these questions. How does spanning tree play in this? Well, remember I said previously that one of the switches in your network will be elected as the root bridge. You do that with the configuration when you get into the switches, and I'll show you how to do that later on. All other switches see that and immediately bow down. Oh, hail the root bridge. You are the almighty center of the network. And so they find the best way to get to that root bridge, and that's the one that they use as their primary connection. This guy's like, hey, I only have to cross one link right here and I get to the root bridge. This guy's like, well, hey, I only have to cross one link to get here and I get to the root bridge. That's great. These links I actually have to go through another switch, so I'm going to block those. And spanning tree has done its job. Now, lag does not play in this part of the situation because those are connections that go between switches. I can't bundle a connection going from, say, switch 1 and switch 2 to switch 3. I can only bundle connections like this and like this. Connections between the same switches. So the lag can play in right here. And since these two switches are sitting right next to each other in a wiring closet, I just use these little 3-inch cables to connect them together. I don't need to run any long strands across the ceiling, right? This is so good. I'm loving this conversation. Now, I know some of you are looking up here at these internet routers and going, well, okay, does spanning tree play here? Bite those fingernails. Spanning tree does not actually play up here because those are not switches. And what's the name of this series? Our eyes are all focused on the switch design. We'll get into the internet routing design later on. Well, I promised at the beginning of this nugget that you will be able to design switch connections for a highly available midsize office environment. I'd love to run through one final scenario with you. The elementary school. A new elementary school has just moved into a vacant building. That'd be this one. They've run approximately 180 cables from various areas of the school to the rack of equipment in the boiler room. I'll show you the floor plan in just a second. They plan to move into the adjacent vacant building over there, which has a mirrored floor plan as the school grows. The school has hired you to install and configure switches for their facility. Determine the number of switches required for the existing building and the model that they should follow for the new building. So here's the floor plan of the elementary school. You can see the various classrooms down there at the bottom. Nurse's office, teacher's lounge. So 180 some cables have been run from all of these locations right here to the center of the boiler room. Right here on the east wall of the building will be the second building that they'll move into that has a mirrored floor plan to this. This is what we need to design. Well, here we are on a blank slate. Right here, I want you to pause the video and on a piece of paper, design this one yourself. Then come back and I'll show you how I designed it. Did you pause it? Hopefully you did. So here's some thoughts. In this series, and actually the previous cabling series until now, I've only introduced you to 24 port and 48 port switches. That's what those circles are supposed to represent. There's 24 individual dots on there, and there's 48 individual dots right there. Those are known as stackable switches. They're always almost 1U in size, and you will see them all over the place in network environments. I'm going to do my initial design using that equipment, because that's what I would have expected you to do. So here's my thought. In the middle of that campus is the boiler room. We would probably have a 2-post rack. And the first thing that I would do is install 2 48 port switches that I would designate as the core switches. We'll call them switch 1 and switch 2. I would mark one of those as the spanning tree root bridge. That means it's the king of the network. All the switches try to find the best way to get to that root bridge. And we haven't gone into too much depth with spanning tree as of yet, but you'll find when we do, you can also set up a spanning tree backup route. We'll call that the queen of the network. When you set up resilient and redundant connections throughout your campus, all the switches will try to get to the king of the network and block any redundant links they have to make sure a loop doesn't occur. But if that switch were to fail, I'd want them to recalculate all their best paths around the network to go to the backup route, or we'll call it the queen. Now, we're not going to get into it in this series, but this is where you would typically attach your redundant routers that get you off to the internet. More on that later. So quickly, with a rough sketch of about how many ports they have, which was 180 ports, I'll pull out my calculator and do 180 divided by 48. That gives us 3.75. So we need, at a bare minimum, 4 48 port switches to be able to service all 180 cables run into that room. And just out of curiosity, I'm going to take 48 ports times 0.25, which is our leftover. So that gives us 12 ports of flexibility. So if we sliced in 2 more switches, we'll just call it switch 3 and switch 4, and cabled all 180 cables right into those switches, we would have 12 ports left over. Now that may be okay, but I'm thinking that's just the cables that feed all the building. I mean, you have those internet routers that are sitting in here. You probably have some servers that are either sitting inside of that rack or somewhere in this room that need to plug in there, and they'll need redundant connections as well. What I'm trying to say is 12 ports really isn't that much left for overflow. Personally, when I look at the cables and I see 180 cables, I want to add a 20% extra buffer for the stuff that nobody really thinks about. The UPS power supply management. The alarm system sitting in the room. The other lines that I would draw in this rack that I really can't think of things for right now. Stuff that all plugs into these switches that you just didn't think of. So if I were to take those 180 cables and do a 20% increase, that gives me 216 ports. That's 36 extra. Totally justifies adding a 5th switch to that rack. Switch number 5. Junk. Now, how are these connected? Great question. With the 2 core switches, I would tie them together with 2 at least individual cables that I would splice together in a lag. Switch 3 would connect one interface to switch 1, one interface to switch 2. Switch 4, the same. Switch 5, the same. Switch 6, not pictured here, the same. Obviously, I'm getting a little bit messy in my drawing, but you get the point. For all the devices that are plugged in here, that gives them at least a +1 redundancy. If our core switch goes down, they can go through switch number 2, which now has the ability to reach the internet routers. And we would often take our servers and split their interfaces between the 2 if we have essential devices that need to be accessed all the time. This is good, and that works. But what about when we introduce the second building? We just put the network design in play for the main building where we've got that rack with the 5 switches sitting in there now. 180 some cables all feeding that room. But the scenario said that the school is planning to move into the adjacent building that has a mirrored floor plan. So in that building over there to the right of this one, I would expect the same kind of design. We've got the rack, we've got the 5 switches, we've got the 180 cables running into there. But then how do you connect that rack in building 1 over to the rack in building 2? Exactly like this. Core switch 1 to core switch 1. Core switch 1 to core switch 2. Core switch 2 to core switch 1, and core switch 2 to core switch 2. And remember, inside of each building, as I said before, each of these switches has redundant connections to core switch 1 and core switch 2. Like that, and like that. Same thing over here. That. And It's getting a little bit messy. And do you see why I put that 20% buffer into our 180 cable calculation? The 180 cables didn't even include all of these uplinks. I also want to make sure that you catch that design is what's needed, not just between buildings, but also between MDF and IDF in the same building. Our scenario assumed that all 180 cables of this building wired to that single boiler room, and that we followed that mirror design over here in building 2. But most of the time in a building of this size, you'll reach a point that running cable from all the way over there in the teacher's lounge to the center boiler room becomes too far. So rather than running all of this cable from far locations, you'll choose another room as the IDF. Get that principal out of there. This school doesn't need one. His office should be the IDF. And you'll install a smaller rack of equipment in here just to wire, we'll say, the west side of the building. And then this IDF over here, who's ever heard of a refrigerator room? IDF, brother. And that IDF would handle all the wiring for this side of the building. You're going to need to connect those racks of equipment back into the MDF, and it uses that same design model. Let's say each IDF only had 2 switches in it. Top switch to core switch 1, bottom switch to core switch 1. Top switch to core switch 2, bottom switch to core switch 2. Do you see the model? And do you see why I wanted to do this scenario with you? Oh man, this nugget has gone a little bit long, but hasn't it been good? Isn't that just... Oh, it's just delicious. All of this design and concept of how these switches should be wired together. A model to expand beyond just a single MDF and a couple switches, all the way out to multiple buildings. Even understanding how spanning tree and lag ports work into that. There's so much more I want to tell you, but it can't be contained in one nugget. We're going to have to expand into more. For now, I hope this has been informative for you, and I'd like to thank you for viewing.